This idea for the principle of inclusion and exclusion was already presented in the previous video. But this time, let's try to really show that this is true. Considering, okay, this not necessarily a proof, but let's say it's a proof. Consider that the intersection of three sets, let's consider finite sets, let's say finite sets A, B, and C, and that, okay, let's assume that we don't know whether the intersections of pairs of these three out of these three, or even the three of them, is known or not known. So let's try to show that from our previously discussed information, we know that, okay, we know that if we're going to consider 2, let's say the union of set x and y, we could write this as the for the cardinality of x plus the cardinality of y minus their intersection, so that we're able to really remove the duplicates, because this item here that we are going to show shows that when we add the 3 and we remove those duplicates, we also need to return the intersection of 3 because it was also removed once we remove any of these 3 here. Okay, so we're going to show that this is really true. Now, let's try to consider that x would be our, let x be actually the union of A and B as a whole, and y would be equal to our C. So that we could actually look into this perspective and have this form here. So we will have, see the white, right? So instead of A union B, you will have to group that. Let's group this one here, and then union C. I am grouping this one here so that we can work on this form, what the item that we also shared before in the previous video, talking about the inclusion of the cardinality of each and then exclusion of their intersection. That would mean this is equal to the cardinality of our x, which is A union B, plus the cardinality of our y, which is C, minus, we have here x is again A union B intersection C. Then let's move forward here. Let's try to first simplify this before this one here. So let's try to look into this one. What would be the identity that is equivalent to that if we have the intersection of one of which is actually a union? We need to try to review the rest of our processes with regards to this, talking about the sets, because it is still equal to, again, A union B, plus you have here C, and take note, C is already appearing here. Part of our target has C. Okay, so we are to continue, minus, again, this is all still on the cardinality, but how do we write the intersection, one of which is union and the other is actually just a set itself? We can simply actually distribute that here. We have minus, okay, take note, we have minus A intersection C, that's 1, union, you have here B intersection C. So we distribute that to form these two forms here now. Now, next part of this is we're going to break this union considering this idea here, and this second is also a union. That would mean, following this perspective, our A union B, or the cardinality of A union B, is just equal to the cardinality of A plus the cardinality of B minus the cardinality of their intersection, right? That is what happens here. But the second one, the cardinality of the union of the intersection of A and C and the intersection of B and C, with this as one set and one set considered, is actually, you have here A intersection C plus the second one, B intersection C, and then minus the intersection of both of them. You have A intersection C, intersection B, intersection C. Okay, so let's integrate them here, and take note the second one is preceded by a minus sign. Please apply the necessary changes. So you still have here, so A union B, we're going to copy this. So you have the cardinality of A plus the cardinality of B minus the cardinality of A intersection B. you will have here plus cardinality of C, right? You still have that. Then this one here, or let me do this one here, plus cardinality of C, then minus the group, the entire result here, minus. Take note of that because a sign may be changed later on. You have A intersection C, sorry, that's cardinality. Cardinality of A intersection C, then plus the cardinality of B intersection C, and then minus the intersection of all of this, A intersection C, intersection B, intersection C. So let me separate them. All right. Now, from this, we can see actually the parts that we're trying to prove. For A is right there, B and C. So we have A, B, and C. We have minus A intersection B, it's right there. We already have A intersection C, B intersection C, also there. And then plus the intersection is yet to be identified from this one. So here goes the next part. So let's arrange first the individual sets. Then we'll have plus intersection C. Then you have minus intersection, cardinality of C, minus the cardinality of A intersection B, applying the negative here, so minus the cardinality of intersections A and C. Still, this is also minus, you have the cardinality of B intersection C. And with this one here, this is actually now plus. As you use the double negative property, you have the intersection of A intersection C and then B intersection C, and then they are under a certain cardinality. So what is this equivalent to? Actually, if we're going to take the intersection of A and C, whatever is that, and then take its intersection to the result of B intersection C, it's just actually equal to the intersection of 3. Okay? Because if you have a Venn diagram here, okay, so you have A, B, C. This is A, this is B, this is C. A intersection C is actually this one here, right? A intersection C. Then B intersection C, this one, is B intersection C. Which of the regions are counted twice or shaded twice is actually this one here. And what is this? Intersection of all 3. So basically, finishing that, you will have here cardinality of A, cardinality of B, plus cardinality of C, minus cardinality of A intersection C, minus cardinality of A, let's change this to B, and A intersection C, minus the cardinality of B intersection C, and then plus this one here. So you have A intersection B intersection C, These are all equal to, again, A union B union C, its cardinality as presented here a while ago. And we have able to show the proof for this statement following this. So this is actually one of the important identities, especially for the proper principle of inclusion and exclusion. We include this, we exclude the intersections, and then again, we add because it was actually removed in the exclusion process. So this shows the identity that we have presented in the previous video. So true, after the this was actually what was presented before was just this portion here for 2. So for 3 sets, this is true, and of course we will have a principle. The principle also will talk about for all A sub i's. Thank you very much for watching.